AI model. ISO 21001 is an international standard for educational organizations that defines requirements for a management system to improve learning services. An input dataset for ISO 21001 compliance in education can include various key parameters. This video is a Sankey diagram visualizing the teaching and learning process, attributed to Pradeep K. Suri. It illustrates the flow of students or learners through different learning modalities, feedback mechanisms, and ultimately, learning outcomes. Let's break it down step by step. Title: Teaching and Learning Process, Sankey Diagram, Pradeep K. Suri, author, researcher, and AI/ML architect. This tells us the diagram is about visualizing the teaching and learning process and is created by Pradeep K. Suri. Components and flow. 1. Left side, Instructors/experts. This section represents the sources of instruction or expertise. Masters faculty, green. PhD faculty, orange. Industry experts, blue. 2. Middle section, Learning modalities. This section shows the different modes of learning delivery. Hybrid, red. Online, yellow. In person, blue. 3. Right side, Feedback and outcomes. This section displays the feedback received and the learning outcomes achieved. Feedback. Neutral feedback, gray. Negative feedback, red. Positive feedback, yellow. Learning outcomes. Low learning outcome, purple. High learning outcome, green. Moderate learning outcome, orange. Flow and interpretation. Connections, the colored bands, flows, connect the different sections, showing how learners move from instructors to learning modalities, then to feedback and finally, learning outcomes. Thickness, the thickness of the bands represents the number of learners or the relative proportion of learners taking that path. Thicker bands mean more learners. Example interpretation. A thick green band flows from master's faculty to hybrid learning, then splits into neutral feedback, positive feedback, and high learning outcome, suggesting that a significant number of learners taught by master's faculty opted for hybrid learning, received mostly neutral and positive feedback, and achieved high learning outcomes. A thinner orange band flows from PhD faculty to online learning, then to negative feedback and low learning outcome, indicating that a smaller proportion of learners taught by PhD faculty chose online learning, received negative feedback, and had low learning outcomes. The blue band from industry experts to in-person learning shows a flow to all three feedback types and a distribution across all three learning outcomes, suggesting a varied experience for learners taught by industry experts in person. Key takeaways. Visualization of learning paths. The diagram visually represents the different pathways learners take in the educational process. Effectiveness analysis. It allows for a quick analysis of the effectiveness of different learning modalities and instructors by examining the resulting feedback and learning outcomes. Data-driven insights. The diagram provides data-driven insights into the learning process, which can be used to improve teaching strategies and learning experiences. Identification of areas for improvement. By examining the flows leading to negative feedback and low learning outcomes, educators can identify areas that need attention and improvement. In summary, this Sankey diagram offers a valuable visual representation of the teaching and learning process. It allows for easy analysis of learner flow, feedback patterns, and learning outcomes, providing insights that can be used to enhance educational practices. Using Sankey diagrams in the context of AI modeling, particularly as Pradeep K. Suri, the author of the diagram, likely intended, can be beneficial in several ways. 1. Visualizing AI model training processes. Data flow in pipelines. A Sankey diagram can represent the flow of data through an AI model training pipeline. Nodes, data sources, example CSV files, databases, APIs, pre-processing steps, example cleaning, normalization, feature engineering, model training stages, validation and testing phases, and deployment destinations. Links, the flow of data between these stages, with link widths indicating the volume or proportion of data passing through each step. Hyperparameter tuning, visualize the impact of different hyperparameter settings on model performance. Nodes, hyperparameter values, example learning rate, number of layers, batch size, model architecture, and performance metrics, example accuracy, F1 score, AUC. Links, the connections between hyperparameter choices and their resulting model performance, showing which configurations lead to better outcomes. 2. Understanding model decisions and explanations. Feature importance, show how different features contribute to an AI model's predictions. Nodes, input features, model layers, output predictions. Links, represent the strength of the connection between features and predictions, often based on SHAP values or similar feature importance metrics. This can help explain why a model made a particular decision. Decision paths in tree-based models, visualize the decision paths taken by data points in tree-based models like decision trees or random forests. Nodes, decision nodes in the tree, splitting conditions, leaf nodes, predictions. Links, the paths taken by data points through the tree, highlighting which features were most influential in the final prediction. 3. Monitoring and debugging AI systems. Data drift, track changes in data distributions over time and their impact on model performance. Nodes, time periods, data segments, data quality metrics, model performance metrics. Links, show how data drift in certain segments affects model accuracy or other performance indicators. Model degradation, visualize the flow of requests through a deployed AI system and identify bottlenecks or points of failure. Nodes, input data, API endpoints, model components, output responses. Links, track request volumes, response times, error rates, and resource utilization to pinpoint areas where the system is degrading. 4. Presenting AI results to stakeholders. Summarizing complex models, use a Sankey diagram to provide a high-level overview of a complex AI model's architecture, data flow, or decision-making process in a way that is easier for non-technical stakeholders to understand. Illustrating impact, show how AI models are impacting business processes or outcomes by visualizing the flow of data and decisions through various stages. Specific example. Imagine an AI model for credit risk assessment. A Sankey diagram could visualize 1. Input features, applicant demographics, age, income, credit history, number of accounts, payment history, loan details, amount, term. 2. Model stages, feature processing, risk scoring, approval/rejection decision. 3. Outcomes, loan approval, loan default, loan repayment. The diagram could then show how different combinations of input features lead to specific risk scores and ultimately, to different loan outcomes. This could help explain the model's decision-making process to loan officers and regulators. In summary, Plotly-Sankey diagrams provide a valuable tool for visualizing complex AI models, understanding their behavior, and communicating their results to a wider audience. They can be used throughout the AI lifecycle, from data exploration to model deployment and monitoring. Input dataset for ISO 21001 compliance in education. 1. Institutional information. Institution name. Accreditation status. Location. Type of education, school, college, university, online, etc. Number of students and staff. 2. Learning environment and infrastructure. Classroom availability. Laboratory facilities. Library resources. Digital learning platforms. Accessibility for disabled students. 3. Curriculum and course design. Course structure. Learning objectives. Credit hours. Industry relevance. Continuous improvement practices. 4. Teaching and learning process. Faculty qualifications. Teaching methods, online, hybrid, in-person. Student feedback mechanism. Learning outcome assessment. Industry collaborations for practical learning. 5. Student performance metrics. Admission criteria. Attendance records. Exam scores and assessments. Dropout rate. Placement and employability rate. 6. Stakeholder satisfaction and engagement. Student satisfaction surveys. Parent and guardian feedback. Faculty and staff feedback. Alumni engagement. Employer feedback on graduates. 7. Governance and compliance. ISO 21001 documentation compliance. Risk management framework. Internal audits. Complaints and grievances handling. Continuous improvement reports. 8. Financial and resource management. Budget allocation for education. Faculty salaries. Scholarship and financial aid. Technology investment. Expiation of the bar chart and pie chart. Overall context, the graphic is titled Teaching and Learning Process Analysis and credits Pradeep K. Suri as the author, researcher, and AI/ML architect. It presents two charts, one showing the distribution of teaching modes and the other showing faculty distribution. Bar chart, Teaching Mode Distribution. Title, Teaching Mode Distribution. X-axis, Teaching Mode, Hybrid, Online, In-person. Y-axis, Count, Number of occurrences or possibly the number of courses/modules. Data. Hybrid, approximately 35. Online, approximately 45. In-person, approximately 45. Interpretation, the bar chart indicates the count for online and in-person teaching modes is the same, and the hybrid mode is less common than the other modes. Pie chart, Faculty distribution. Title, Faculty distribution. Categories. Master's faculty, green. PhD faculty, orange. Industry experts, blue. Percentages, each category is labeled as 33.3%. Interpretation, the pie chart shows an equal distribution, roughly 1/3 each, between master's faculty, PhD faculty, and industry experts. Thank you.